It's time for another math easy solution to discuss further into applications of integrals, and now look at further into area of a surface revolution or surface area, and look at example 3 of the example series. And in this example, I'm going to solve it using, well, one solution we'll call it solution 1, where we use y in terms of x. In this case, will be y equals e to the x. In the next video, I'll go over solution 2, which is the other way around. We'll have x in terms of y, and this will make more sense as I get through this example. Basically, the example we're going to cover today is this one here. States find the area of the surface generated by rotating the curve y equals e to the x from x is 0 to all the way to x is 1 about the x-axis. So the first step to do is to, well, let's just graph this to get a better idea of this function. So if we draw the x and y axis like this, draw this a bit straighter. So x, this is y right here. Now this function y equals e to the x, when you plug in x is 0, you get e to the 0, which is just 1. And it's an exponential function, it just goes up exponentially. So this is from 1 to 0, and this is the curve y equals e to the x. So we get the, we can generate a surface by rotating this about the x-axis right here. So rotate this curve about it. Yeah, so now if we just rotate this about, as just draw it as a circle around it, so this point becomes over here, just reflected across, and then it's something like this, and this part here is exponential like that. I'll draw it 3D, so behind it shows 3D, and then here we get something that looks like this, and this shape that we generate is this one across all the way around this shape right there. So now in solving for the surface area, well, let's just recall the surface area formula, which I covered in my earlier videos. So surface area formula, draw this better, surface formula, surface area formula right here. And if you recall, basically we'll call this S. So let's call this area S, the surface area. And like I showed before, we defined S is basically it's summation or the integral of, well, whenever you look at a small section here, circumference, just to get a better idea, I'm going to write it like this: circumference times it by arc length, and this circumference times by arc length. These are for a very small section. So just to get a refresher to illustrate this, let's take a random section here, and we'll consider this little piece, this arc length ds, and we'll consider it as infinitely small. So just pretend it's really, really small. So we're getting a slice of this shape right here. And then draw this in 3D like that. So when you have a really, really small section like that here, and this is the area we're going to solve. And this is this is pretty much a circle with a arc length like that. So this radius right here, we'll call this y. So the radius is just y because, and this is just anywhere in between inside this arc length, but what's infinitely small, it's the same as if you had it from this point or this point, doesn't matter. It's really, really small. So if that's the radius, so the circumference is just 2 pi y. So this equals to 2 pi y in our case, times it by the arc length, which is just ds. So when you multiply the circumference by this section, you get that area right there, or the surface area. And basically, where I explained in as I explained in my earlier videos, the formula for this ds, or this arc length, is equal to 1 plus dy over dx squared dx. And in this case, we'll call this solution 1. We'll use this one for this video. But like I showed before, and also if you rearrange this, you could also write this as, or ds is equal to 1 plus dx over dy. So it's the same thing, but this is just writing in terms of having a dy right here. So this one here, put this in a bubble. I'll call this solution 2, and we'll solve this in my next video. So for this particular solution that we're doing, solution 1, everything's going to be in terms of dx right here, or x, and we'll write y in terms of x as well. So the interval that we're integrating is going to be on the x-axis, so from 0 to 1. So 0 to 1 in our case. So now if we use the solution 1 formula there for the arc length, let's just start solving this. Well, we know y equals e to the x. Now the derivative, dy over dx, that's just, well, of this is just itself, ex. And yeah, the derivative of e to the x is just itself. So now what we get is ds equals to, well, 1 plus dy over dx squared dx. This equals 2, and you plug that all in. 1 plus, and then you have e to the x, but it's squared, you just put that in front. So e to the 2x doesn't change anything. So now that is ds right there. So now we can just plug this all in. So we have the surface area is equal to the integral from 0 to 1 of 2 pi y ds, which equals to, and you take this 2 pi out as a constant, integral from 0 to 1 of e to the x, and then 1 plus e to the 2x dx, like that. And now in solving this one, this integral is not that straightforward, but what we could realize is that this e to the x in front, we can get rid of it by using a substitution, because if we substitute for this ex, when you take a derivative, you still get it, so you can cancel it, and I'll show you how that's done. So basically use substitution, and this will make more sense as I go through it. So use substitution. So in this case we let u just equals to e to the x, so that the differential du equals to e to the x and then dx, like that. We solve for dx equals to du over e to the x. So that's when you plug in this dx inside here, you can cancel these e to the x's, and also just write e to the x is just u, so we have du over u. So that's what dx is equal to. So we have everything, we just need to change the interval. So at x equals to 0, we have u equals to e to the 0, which equals to 1. And then when you have x is equal to 1, you have u is equal to e to the 1, which just equals to e. So putting this all together, we have the surface area S equal to, well, let's write 2 pi out in front. So 2 pi integral from 0 to 1 of ex 1 plus e to the 2x, just write for completeness sake, equals to 2 pi, and then 1 to e of u times 1 plus, this is going to be u squared, du over u. That's what the dx is equal to. So when you just cancel these out, so the u's cancel, so we're left with 2 pi integral from 1 to e of 1 plus u squared du. Now this function is still not that straightforward in solving it, but if you recall from earlier videos on trigonomic integrals, trigonomic substitution for integrals, this is a pretty familiar form that we have right here. So basically, if we now we use trig substitution. I'll show you why, and you can learn more about trig substitution or trigonomic substitution in my earlier videos. So the reason we'll do this is, well, simply because, well, let's just circle this. Actually, screw that. Okay, so since we know or also recall the trig identity, so recall the trig identity which I covered earlier, 1 plus tan squared of x is equal to secant squared of x. So since this one here, we know this identity. Now if you compare it with the function, compare with right here, this 1 plus u squared right here. So we can get rid of it if we use a substitution where u equals to tangent, and then we could get rid of this 1 plus and just have a this trig function secant squared, and then you can square it to make it even simpler. So what we do is let u equals to tan theta. We can't use x because I already have that. So in this case, we let u equals tan theta, and also we have to define this theta so that it's a one-to-one function. So we'll define it from less than pi over 2 greater than negative pi over 2. And the reason for this is so that we have a one-to-one function. And again, you could learn more about this in my earlier videos on one-to-one functions and trigonometric substitution for integrals in the video links below. And also just go further, if we graph this out, let's call this theta, this is u. The graph for tangent looks something like this, where you have an asymptote here at pi over 2. This is u equals to, I'll just write it here, u equals to tan theta. So as asymptote here, that's why we have a less than pi over 2, an asymptote all the way across here at, this is negative pi over 2. And it's periodic with any trig function, so it just keeps on going and going like this. So you have another one, and you have another one like that. Keeps going and on, and then we have to make sure it's one-to-one, so we define it between these intervals, because if you were to draw a horizontal line all the way across it, I'll draw that in blue. So if you were to draw a horizontal line across it like this, what we have to ensure is that there's, for every y function, every y value, there's only one x value. So that's why we can't keep using these. So we have to define theta between these two across here, so we only deal with this curve. So now what we get when you, basically when we plug it into the substitution, what we get is this 1 plus u squared equals to, well, square root 1 plus tangent theta squared, like that. Now this part equals to, using that substitution right here, this is just secant squared. So this equals to square root of secant squared theta. But now since we have the square root, everything must be greater than 0 here. And also when you have the squared, secant squared, or this, then square rooted, since the secant inside could be plus or minus, you have to make sure, then you'd say, yeah, it could be plus or minus. So, but in this case, we have to make sure it's greater than 0. But in fact, when we just look at the function, the function secant theta, it is greater than 0 in this interval. So in this interval, this is basically secant theta, like that. Let's write that neater. So this secant theta it goes up like this. If you recall, it looks like it's just 1 over cos, and in this case here it goes down like that. But in this case, it's always positive. So since it's always positive and the square root, everything needs to be positive, we are fine with this one. So thus, when you square root it, this equals to secant theta. And this right here is greater than 0 for theta is less than plus pi over 2, greater than pi over 2 negative. So we are fine with that case. So we have that. And now what we have to solve is the other parts of the substitution, where you have du. So u equals to tan theta. Du is, just recall, the derivative of tangent is just secant squared theta. So equals secant squared theta, and then the d theta always added for this differential notation. So we have this like that. And now the other thing we have to do is change the intervals. So at u equals to 1, what we have is, this 1 equals to tangent theta, and recall definition of tangent, this is just opposite over hypotenuse, over adjacent for tangent by definition. So this is what it equals to, or sine over cos, and this, we have an exact trig function. You can learn more about this in my earlier videos, but let's just solve it here. So if it's opposite over adjacent equals 1, this both has to be 1. So 1 over 1, and that's just 1. So if you were to draw a right angle triangle, so this is opposite adjacent of a right angle triangle. So this angle theta, we have opposite is 1, 1. This is not the scale. So if you were to draw it across, this is 1 and 1. This is a square. So this is a square. This angle is 90 degrees. Half of this is just pretty much half of it. So this equals to 45 degrees. So that's 90 degrees or 45, or in radians, this is just pi over 2 divided by 2, which is pi over 4. So the angle is pi over 4, and we're going to be dealing with radians as always, unless otherwise stated. So that's what we get in this case. So now add u equals to e. Add u equals e. There is no exact trig ratio, so we have e equals to tan theta. So in this case, there's no exact ratio that we have for this, so let's just write this as theta is equal to inverse tan of E. And we'll call this, just to make it easier to write, call it alpha. And we'll deal with it like that. So now we have everything. Now we can just plug in everything together. So S equals to 2 pi, integral of 1 to E of square root 1 plus u squared du. Now this equals 2 pi still there. Integral is going to be from now pi over 4 to alpha. And this square root 1 plus u squared is equal to secant theta. And then du is equal to secant squared theta d theta, which equals 2, just simplified further, integral from pi over 4 to alpha of secant cubed theta d theta. And now, although this integral looks, it's a bit simpler than we started off with, again, the derivation of this integral is still complicated, but I went over it in my early video, so instead of reinventing the wheel, basically recall from my basically trigonometric integrals video, so trig integrals example 8 video, which I covered earlier. The video link is in the description below. So on example 8, I solved the integral of secant cubed x dx, and I solved it as equaling to 1/2, and then this is going to be secant x tan x plus ln of absolute value secant x plus tan of x, and then plus a constant c. Yeah, so if we just recall this derivation for that, and then we can just plug this inside there. So we have s is equal to, well, we have 2 pi from pi over 4 to alpha, pi over 4 of alpha of secant cubed theta d theta is equal to, plugging this all in, this 1/2 cancel, so we're just left with pi, and then secant, so we'll be switching everything with theta, so we have the secant theta tan theta plus ln absolute value of secant theta plus tan theta, and this is absolute value, and this is from pi over 4 to alpha. So we have this, now we just evaluate it. Pi is equal to, this is going to be pi, plug in theta, so plug in alpha, secant alpha times by tan alpha plus ln of secant alpha plus tan alpha. Let's just write it like this. And then, before continuing further, I just want to go over this absolute value sign. Since we're dealing with secant and tan theta right here, so let's scroll all the way up over here. For secant theta, it's always positive in this interval, and for tan theta, since e is a positive number, whenever we have a positive value here, so whenever this is positive, the angle as well is going to be positive right here. So in this case we'll have alpha somewhere across here. So alpha is greater than 0 because e, the value e, is 2.7818 or whatever, so it's somewhere around here, and so that makes it positive as well. And also pi over 4 is also positive. And since we're integrating from pi over 4 to this alpha, then we're just only dealing across in this positive side. So that means we could just get rid of this absolute value sign right here. So this whole thing is going to be in terms of, well, positive values. So it doesn't matter if it's absolute value, it's always positive anyways. So, and then continuing further, subtracted by secant pi over 4, tan pi over 4, plus ln of, this is put in the bracket like that, plus ln of here, which is secant pi over 4 plus tan pi over 4. put this another one like that to cover this one. So that's what we have, and now let's begin solving this. First, let's recall that alpha is just equal to inverse tan of E. So rearrange this, we have tan alpha is equal to E. So this right here equals to E, this equals to E, and now this secant alpha, well we know that 1 plus tan alpha like that squared is equal to, this is secant squared alpha. Just using that same trig identity which I showed above. So this means that the secant alpha is equal to, just square root this, and again just plug in the E inside, so we have 1 plus E squared. So this equals to 1 plus E squared. And again, the secant is always positive. In our case, we're only dealing with positive because this could be plus or minus whenever you square root something. So we have this value right there. So we solve for this one as 1 plus E squared, all square rooted. And now the next one is this pi over 4 values. Also recall that we also showed that tan of pi over 4 is just the exact trig ratio of 1, so that just equals to that. And if you look at a triangle like this, absolute value, this is opposite over adjacent, this is 1 over 1, and this is pi over 4. So if you use the Pythagorean Theorem, right here is just square root 2, so it's 1 squared plus 1 squared all square root. So this is 1 squared, and then what we know is that basically secant pi over 4 is equal to, well again, secant is just definition 1 over cosine pi over 4, which equals to, I'll just move this around here to get out of the way. This definition of cosine is just adjacent over hypotenuse, but since at the bottom we have adjacent and then hypotenuse on top. Hypotenuse, I think that's how you spell it. So in this case, adjacent is 1, hypotenuse is square root 2. So we have square root 2 over 1, which just equals to square root 2. So we can just plug this all in together right here. So now we have s is equal to, s equals 2, let's scroll up, we have this pi, so we have pi times it by secant alpha, which is 1, which is this value right here, so we get, and I'll put the e in front, so we have e times 1 plus e squared, and that's because we have this one right here, and then we have ln of, and I'll put the e in front as well, so ln plus, then plus ln e plus 1 plus e squared, like that, and then last we have this subtraction, so we subtracted by, this is secant pi over 4 is going to be square root 2 times 1, so negative square root 2 minus, multiply the negative inside, now we add those up now. So now we have minus ln, and then this is going to be the addition of the 2, so we have 1 plus square root 2. And this is our answer right here. Yeah, now if you were to plug this in the calculator, this is pretty complex. I think here I plug in the Google calculator, you have pi times e times square root 1 plus e squared plus ln e plus square root 1 plus e squared minus square root 2 minus ln and the square root 2 plus 1. I think I put in all the parentheses correctly in brackets, so you get about 22.94, but if you can double check and make sure if I got this right. So this equals to roughly 22.94. Put this like that. And yeah, that's pretty much it for today for this video. Hopefully you followed along. It's pretty extensive, and I had to use a couple recall solutions and recall different theorems such as substitution and trigonomic substitution for integrals. But it's pretty interesting on this, and then next video I'm going to go over solution 2 and show that it's slightly easier in this case. Anyways, hopefully you learn. Like always, you can download these exact notes in the link below, and thanks for watching, and stay tuned for another Math, easy solution.